Good afternoon, everyone, and thank you for attending our Advanced Rigid-Flex Circuit Construction webinar. My name is Keith Rujo, the Director of Marketing here at Epic. Before we get started, I just want to let you all know that you will be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel located into the webinar control panel on the right side of your screen. If we don't have time to go through all the questions, we'll be sure to get back to everybody by email. Also, we will be recording this webinar and posting it on both the recording and the slides on our website and YouTube channel. Our presenter today is Paul Tomei, our Flex and Rigid Flex product manager. Paul has over 30 years experience in the electronics industry, being involved in all aspects, including sales, engineering, and manufacturing. He has worked with PCB and equipment manufacturing, and also has been an owner of his own engineering and test service bureau. Paul's main duty at Epic is overseeing our entire Flex and Rigid Flex product line with a hands-on approach to customer technical support. He is often directly involved in many of the more complex Flex and Rigid Flex projects from the beginning of conceptual stages all the way to delivery. He works directly with customers on either specific design requirements, making sure the product is designed correctly, or troubleshooting any issues that may arise during the process. So without further ado, I will pass it over to Paul.
Thank you, Keith. Good afternoon, everyone, or good morning, depending on where you are, and thanks for joining us today. As Keith mentioned, the topic today is Advanced Rigid Flex Circuit Constructions. So today's rigid flex materials and constructions allow for a pretty wide variety of what would be defined as advanced design configurations. And these options create some significant opportunities to achieve higher levels of both design integration and packaging density within a given design. Some of the options that we're seeing these days are substantially higher flex layer counts. We're seeing many designs with blind and buried via structures, designs with integrated zip connections. We're seeing components mounted into the flexible areas as well as on the rigid sections. We're seeing asymmetrical constructions, and we'll get into that detail a little bit further on. Designs where the flex areas require shielding for EMI or RF considerations. And we're also starting to see designs that have varying thicknesses between the different rigid areas. So in this webinar, we'll introduce and discuss some of the benefits and applications of some of these more common advanced rigid flex constructions that we're seeing. But having said that, there are many additional configurations and combinations available beyond what we can cover in the scope of today's webinar. So the agenda, we'll first touch upon what's deemed to be a standard construction to kind of give us a baseline to build upon. And then in the advanced constructions, we'll talk about odd layer count constructions, asymmetricals, varying flex layer count designs. We'll touch on integrated zip connections, blind and buried vias, air gap flex constructions, multiple rigid area thicknesses, and again, shielded flex layers. So to start off and give us a base for this webinar today, a standard rigid flex construction is loosely deemed to be one that has a symmetrical construction, i.e. the flex layers are located in the center of the construction. Even layer counts in both the rigid and the flex layers, and the design does allow for impedance control. So here's a graphic of a standard rigid flex construction, and you can see in the two thicker areas, which are the rigid areas, it's an even layer count. In this example, we have 6 layers, but that can vary anywhere from 4 to 16 and on up. But the key element is that the flex layers are located in the center of the construction. So moving on. The first construction I'd like to talk about is odd layer count constructions. Now, you may not deem this to be advanced, but it is not very common, or it's not commonly aware of in the bulk of our customers, given that they come from the majority of them from a rigid board design world where even layer counts are always required. And there are advantages to odd layer counts in rigid flex constructions, and they are very much manufacturable. So the first example here is a 7-layer rigid with 3 flex layers. Flex layers are located in the center and allows for some characteristics that you would not be able to achieve otherwise. And we'll get into that in a little bit more detail in a minute. The next construction is a little bit more on the simpler side, where there's, in this example, 5 layers in the rigid and only 1 layer in the flex. So the applications for these layer counts, going back to the first 3-layer example, is the primary application that we see is that this now allows for 2-sided shielding in the flex areas, primarily driven by strip line impedance control. There may be some RF and EMI considerations, but you can create that strip line impedance control configuration within the flex now. So you'll have your ground, signal ground construction within the 3 layers of flex. Odd layer counts, as shown in the previous 2 examples, apply to both the flex and the rigid areas, and they're independent of each other. So you can have an even layer count in one and an odd in the other if the design requires it. Primary advantage is that it minimizes the flex area thickness, which in turn provides improved flexibility, increased mechanical bend capabilities, and in turn, mechanical bend reliability. The constructions are compliant with IPC 2223C, which ensures that the parts have both short-term and long-term reliability. And lastly, to a certain degree, odd layer counts can help reduce the cost of the design by minimizing the total number of layers, of flex layers specifically, required in the design. Next construction we wanted to talk about is asymmetrical ones. And the applications for an asymmetrical construction are typically driven by some very convoluted impedance requirements, where you have some widely varying dielectric thickness requirements within the design, and also by blind via constructions, where the asymmetrical design construction allows the blind via aspect ratio to be reduced, which in turn improves the manufacturability and reliability of the parts. There is one consideration in that, given that it is an unbalanced build, so to speak, is that there may be some warp and twist that occurs within the assembly array, which then may require a hold-down fixture to allow the assembly arrays to be transported through the assembly process. So here's an example, a pronounced example of an 8-layer asymmetrical construction. And you can see that the flex layers are no longer located in the center of the design. They're shifted down towards the bottom. Again, a very manufacturable configuration. There are no manufacturing concerns, just the previous one I mentioned, that some warp and twist may be induced in the assembly array. Another type of construction that we see on a fairly regular basis is where the flex layer count varies between rigid sections. So if you had 3 rigid sections, you might have 3 or 4 flex layers joining 2 of the rigid sections, but only 1 or 2 layers joining the second to the third. And there's quite a variety of configurations available. This type of construction, it is preferred to use an air gap flex layer construction. Again, air gap construction is one that we'll cover a little later on in our webinar. And the following is an example where between the first and the second, starting from left to right, between the first rigid section and the second one, we have 4 layers of flex. But between the second and the third, we've only have 2 layers of flex. Now layer 2 and 3 flex, the first top pair, does extend into the final rigid section and does exist within that rigid section for routing purposes, but it does not transcend or cross between the 2 sections. Primary advantage of this is in the reduced flex section, given that the number of interconnects do not require the additional layers, by reducing it down to 2 flex layers only, you significantly improve the bend capabilities of this type of construction. Another common one, and this is probably of the more advanced rigid flex constructions, this is probably the most common one that we see, and that's where a zip tail is integrated into the rigid flex. So this in turn eliminates the need for the zip connector to be mounted onto the rigid board, eliminates the need to have a separate flex circuit. It reduces the real estate requirements in the rigid area, should it be a high density design where real estate is at a premium, or if it's a very slim, thin design where the height requirements of a ZIF could not be incorporated. There is an element of improved reliability through the elimination of points of interconnect. You don't have that ZIF connector. You don't have the ZIF connector to flex interface. And in this type of configuration, there are a very, very wide variety of configurations available. So here's an example of a very straightforward 3-layer integrated zip tail construction. And as you can see, the zip tail that extends off to the right does have the additional polyimide stiffener required to achieve the specific thickness in the zip finger contact area that is required by the zip connector. This configuration can also be combined with multiple layers of flex, 2, 3, 4 would be about the practical limit because it then becomes difficult to meet the zip thickness requirement. But we typically see it in 1 and 2 layer of flex configurations. The next type of construction that we're going to talk about today is ones involving blind and buried vias. The applications are very similar to that of rigid boards, typically driven, and from our experience in our marketplace, typically driven by high density BGA applications that require via and pads. This type of construction may require an asymmetrical construction if the blind vias are required to have an interconnect to the flex layers. The configurations may be limited by the number of sequential lamination cycles that the designs require. Multi-layer rigid flex can only accommodate a limited number of lamination cycles before the dimensional tolerances of the materials and the manufacturing methods prevent the layers from being effectively registered to one another, so there are some limitations in that area. And in the same fashion as rigid PCBs, for via and pad applications, via fill and capping is available. So in our construction example, in the right-hand portion, the black sections for this example define the via structure. So in this case here, we have a blind via that goes from 1 to 2, an additional one from 1 to 3, a buried via from 3 to 6, and then a blind via coming up from the bottom from 8 to 6. And you can see that this is also an asymmetrical construction where the flex layers were moved down towards the layer 8 side of the design in order to minimize the aspect ratio of the blind via and in turn allow for the manufacturing of a reliable part. We mentioned earlier air gap constructions, and the flex layer air gap construction has the flex layers configured as independent pairs of 2. So obviously this applies to designs that have more than 2 layers of flex. This is a preferred construction for four or more flex layers, primarily due to it allows the design to meet IPC 2223C design guidelines without exception. This type of construction results in that there are no flexible adhesives present within the rigid areas, which in turn provides the reliability of the via structure and doesn't create any issues during the assembly or long-term operation of the part. There's an additional advantage of the air gap construction in that having the flex layers as individual pairs of two substantially improves the flexibility of the flex section. The flex layers essentially are bending independent of each other and provides a substantially higher degree of flexibility where you have two pairs of two versus one structure of four laminated together. So in our construction example, in this case here, we've got 6 flex layers, all configured as air gaps. So you can see that each flex pair has a coverlay on both sides. Then there is a small air gap, and then so on. The next pair, same construction, 2 flex layers, coverlay both sides, and so on down to the third pair. Very much a preferred configuration. If this design was attempted to be done with all 6 layers bonded together, it would not meet IPC 2223C. There would probably be some very significant via reliability issues, and the flexibility of the flex section would be very much limited, almost to the point of not being functional. Now moving on to multiple rigid area thicknesses, and this is a very convoluted type of construction. We've seen some examples, we manufacture them, but if this is a consideration, then I would strongly suggest that you have a conversation with either us here at Epic or your supplier of choice. So in this type of construction, the rigid areas have different thicknesses. Practically, you're limited to 2 rigid thicknesses as a maximum. There may be some limitations into what those rigid thicknesses can be due to the materials required for the construction. Ultimately, this is a very costly type of construction. In layman's terms, you're essentially manufacturing 2 boards to get 1. So in our construction, in our profile here, you can clearly see that the left side rigid section is substantially thicker than that of the right side. The flex layers transcend all the way across. There are plated through holes and vias in both sections, although they're not shown in the left-hand section here. The thinner section does, as I mentioned, have some limitations as to the thickness because there has to be a degree of, there has to be some commonality in the materials. The pre-preg thicknesses, for example, on this side need to be the same, on the left side need to be the same as the right side. If we were to have an additional cores on the right side, they would have to mirror that on the left side. But ultimately, during the manufacturing process, we manufacture this as a 4-layer design, which would encompass layers 2 to 5, run it all the way through to the end of the process, even through electrical test. The only thing we wouldn't do is create the outer profile. We then take that design virtually back to the beginning of the process and add layers 1 and 2, or sorry, in this case, 1 and 6, or if there are more layers, add those and then run it all the way through the process again, through drilling, through plating, through surface finish, and so forth. And then finally at the end, create the final outline. So it is a very, very expensive process. We have seen some applications that absolutely demanded it. We've seen other applications where the customer entertained this, but we were able to propose alternatives that met their design requirements, and we were able to save them some cost. The last type of construction I'd like to cover today is that of shielded flex constructions. And the shielding in this case here is not copper layers. It's utilizing specialized films that were developed specifically for shielding on flex. Two of the more common brand names that we use are Tatsuda from Japan and A+ from China. And these films allow for very, very effective EMI and RF shielding without the added cost of copper layers. As I mentioned, reduces the cost, results in a much thinner flex area construction for improved flexibility. These shielding films are laminated to the flex area coverlays, and they interconnect, and they're not floating grounds. They actually ground out through to the circuitry of the design. They're interconnected through selective openings in the coverlays, and the films themselves have an electrically conductive adhesive pre-attached to them. So once they're bonded on, the adhesive then goes through the coverlay openings, bonds onto the exposed ground, and ground out the shield layers. So in our example, 4-layer design, 2 layers of flex. In the flex area only, you can see the shield layers laminated to the external sides of the coverlay. Again, very cost-effective, more cost-effective than adding additional copper layers, substantially greater flexibility and mechanical bend capabilities, I should say, as opposed to adding copper layers. It's a configuration that we propose on a fairly regular basis to our customers where there's EMI and RF shielding requirements. It's proven to be quite successful. So in summary, the combination of today's rigid PCB and flex circuit technology has created a very, very wide variety of rigid flex constructions that can add a significant amount of functionality, design integration, and overall packaging reduction to a design. The majority of the specific constructions that we reviewed today can also be combined together to in turn create an almost endless number of configurations. Keith, I'll pass it back to you.
Thanks, Paul. While Paul reviews some of the questions that came in, I just wanted to briefly mention to you some of the additional PCB-based products we offer here at EPIC. Our custom battery packs, high reliability user interfaces and cable assemblies, Flex Rigid Flex PCBs, our core product circuit boards, and our newest addition to our product line, our RF product solutions. Next slide, please, Paul. We also have facilities based around the globe that specialize in each one of our products. So for our battery packs and power management, located out of Denver, Colorado, our smart user interfaces are down in Largo, Florida. Flex and Rigid Flex is up in Toronto, Canada. Our RF products are based here in New Bedford, Mass, also in our Largo, Florida facility. Cable assemblies are done down in our Largo, Florida facility as well, and our printed circuit boards here in New Bedford, Mass, and also in Shenzhen, China. Next slide, Paul.
All right. Well, thank you for your questions. I picked out 3 that I think are very relevant, and they're also fairly common questions that we entertain from our customers. So the first question is, can components be attached to the flex areas in a rigid flex design? The answer to that is yes, it can. Similar rules pertain that apply to a flex-only design that have components, in that stiffeners are recommended in order to support those component areas. There can be, depending upon the design, some assembly considerations, because typically the flex layers are located at a lower level in the construction than that of the rigid sections. So then a strategy needs to be developed in order how to paste, pick and place, and reflow the components in that reduced area. There are some techniques out there to accomplish that. with tooling plates that raise the flex section up to the plane of the rigid sections to allow for for solder pasting. So it is fairly common. It is fairly common. Second question, and this one is one that we see on a somewhat regular basis. And the question is, are bookbind rigid flex constructions available? To define a bookbind rigid flex is one where the flex layers, in this case, there'll be multiple pairs, for example, 4 or 6 layers total configured into pairs of 2 in an air gap construction. But each of those pairs is of a different length. They increase in length as you go through the stack. And what that allows is once the flex is bent into its position, that then accommodates the varying lengths and allows for many layers of flex to be then bent into position. Bookbind rigid flex constructions are getting fewer and fewer and further between from our perspective. They're very expensive constructions to manufacture. There are some potential solutions to avoid it. We see the demand for bookbind and also the supply chain for bookbind diminishing somewhat year over year. But they are available, but they are extraordinarily expensive constructions to manufacture. And the last question I wanted to get to today is, are there limits to the shape and size of a rigid flex design? And the answer is yes, there are some limits that apply. The limits will be dependent upon the technology level of the design. If you're doing HDI with blind and buried vias, that will tend to significantly limit the size of the shape. That limit is primarily driven by the dimensional tolerances of the materials, of the flex materials, and of the manufacturing process. In terms of shape, there are, probably the one that comes to mind most is when the customer essentially creates a island rigid section that is completely surrounded by flex. And that can create some manufacturing issues where it just can't be done. So there are some size and shape limitations. The vast majority of rigid flex designs that we see are less than 12 inches in overall length and probably less than 8 inches in overall width. That would probably encompass 96 to 97% of the marketplace as we see it. So there are some limitations. So if you do have something that's a little outside of the norm, both in size and shape, then having a discussion with your supplier or contacting us here at Epic to review your requirements would be a good practice. As Keith mentioned, we've got a number of other questions that come in. We'll make sure that we answer all of those, get back to you via email on all of those. Thank you very much for attending today. We appreciate it. Take care, everyone.